Good morning, everybody. Welcome to a wonderful morning at Chem 1211 with your host, me, Dr. White. Seems like a Monday, but it's really Tuesday, but it feels like a Monday. Why? Because I'm going to put my garbage out tonight. Normally, I would have done it last night, but because of the holiday, uh, seems like a Monday, but it's not. All right, let's get to work. What are we going to do today? First of all, there's something I forgot to teach you, two things that I'll cover. Next, I'll go through the problem sets for chapter 3. Yes, there are two of them. Why? Because I forgot to put temperature in the first one, and I made it a separate one. And after that, I'll do some lecture from chapter 9, and then we'll do our first lab. Yep, our first lab. And I'll go through that, and we should be done by midnight. No, today, because I lost time yesterday, we'll go till about 11, give or take 10 minutes, maybe 10:50. So I better get going. Oh, more than one. First of all, if you haven't uploaded the contract, safety contract for COD, you should, because if you don't have it done by next week, you'll get 0 points. I think earlier this morning, I think about 20 out of 24 of you have already done that. Next, don't forget, a lab is due today that we did last week. That's the safety lab. And you upload it to Blackboard as a single PDF file. And also over the weekend, I added some stuff, including a type, not cursive, test number 1 review. It's both as a Word and a PDF file. That's available. And also, I didn't have last time in the safety contract, so I put it in, or when we went through the safety lab, and that is the safety information for doing labs from the company. Was it Carolina company or whatever they're called? But I should tell you, the labs look pretty good considering what we did in the past with a kit, which was, well, how should I put this politely? Years ago, I hired a student for a summer as a summer employee. We do that at certain companies. And she was probably the sweetest, most innocent, nicest person I've ever met in my life. When she'd get mad, she'd say, "That's awful." One day she was really upset and she said, "That's awful, awful." Yeah, she was the sweetest person I've ever met in my life. And the previous, not the one we're doing this semester, but I think it was 2 summers ago, the 1211 chem kit was awful, awful. Ours that we're doing this semester looks pretty good. All right, let's go through and let me cover stuff that I didn't in the past. Thumbs up, people. Can you see my whiteboard? Thank you, Jasmine. All right. When we're talking about a mixture, there's 2 types of mixtures that I forgot to mention because I didn't have a slide for it, bad Dr. White. And one type is homogeneous. That's the same. That's the same throughout. And I'll explain this in a minute, maybe less. And the other type is heterogeneous. which is not the same throughout. So there's homogeneous and heterogeneous. What would be an example of homogeneous? Well, if you took sugar and water and shook it up real good and mixed it, the sugar would dissolve, and throughout the whole solution, like if I had my water bottle here, if I shook it up real good and dissolved the sugar, you could do the same thing with salt. It would be the same throughout. Right now, you're all breathing, I hope. And if I'm here, I'm getting the same amount of oxygen and nitrogen in the air. If I walk over by my door, by the way, that's stuff for my next project. I do electronics as a hobby. If I walk over to the door, it's going to be the same amount of oxygen and nitrogen. It's homogeneous. If you make tea, I'm a tea drinker, you know. In fact, I should have some right now. Oh, is that good? Blueberry tea. Second cup, first cup was vanilla almond. Throughout the whole tea, if I were to stick a straw in the bottom and sip some, it would taste the same as if I did tasted it from the top. That's because it's the same throughout, homogeneous. Another thing that's homogeneous, it better be when you buy gasoline. Gasoline is a very complex mixture of different substances, and it's the same throughout. When you're pumping it into your car, there's a tank underneath the gas station that holds that type of gasoline. And you don't want it separating and not be the same throughout, or it'll ruin your car. So that's an example of homogeneous, the same throughout the whole mixture. Now, the other type is heterogeneous. It's not the same throughout the whole mixture. Remember, we're talking about mixtures when you put two or more substances together. Now, what would be an example of a heterogeneous mixture? I won't do this, but if I had water, like my bottle of water, and I put in sand, no matter how hard I shook this, the sand would go to the bottom and the water would be on top. It's a mixture, two different things mixed together, but it's heterogeneous. The sand's at this bottom, the water is at the top. It's not the same throughout. Now, as I said, first day of class, you learn a lot about me personally and my family too. And my mother's favorite salad dressing when we were at home was the wishbone salad dressing, oil vinaigrette. Have you ever seen an oil vinaigrette dressing in a bottle or whatever container it's in? You'll see they're two separate layers, one on top of each other. The top one is the oil, vegetable oil. The bottom one is the vinaigrette. Vinegar is mainly water. So the water, you shake it up, you put it on your salad dressing, on your salad, don't on your salad dressing, put it on your salad, and it's pretty good. I've learned how to make my own much better, much better. But anyways, when you put the bottle down, if you wait 5 minutes or less, it separates because it's heterogeneous. What would be other heterogeneous solutions? Not solutions, mixtures. Well, here's one I wouldn't do, but if I had a bucket of water, or here's a good one. How many of you have ever thrown coins in a fountain? I've done it in Europe too. You know, it's supposed to bring good luck and get your wish granted. But anyways, if you take a handful of coins and put it in a bucket of water, the coins are going to go all the way to the bottom. And it'll be a mixture because you got water in the coins. But, oh, I just happened to have a coin here. I was cleaning up a quarter. It would go to the bottom. And that would be heterogeneous. So you should know, I forgot to talk about it, bad, Dr. White, bad. now making up for it. You should know there's two types of mixtures: homogeneous, the same throughout; heterogeneous, not the same. All right, the other thing I forgot to talk about is formulas in chemistry. And there are two types. Now, empirical, and I'll never ask what's the definition of an empirical. This shows how many atoms and what type and how many. Structural shows that, but also the structure. This one we won't be using in this class. That's when I teach organic, but we will be using empirical. So let's talk about empirical formulas. This is water. And notice it has the symbols for the elements, chemical symbol, hydrogen and oxygen. But here we have subscript to the right of the chemical symbol of hydrogen, a 2. And that 2 tells us we have 2 hydrogen. And notice there's nothing to the right of the oxygen and 1 oxygen in water, which means there's 3 atoms in water. And this is called sodium chloride. Otherwise known as salt or table salt. And if you ever go out with a bunch of chemists to lunch or dinner, breakfast, and I've done this more than once, could you please pass the NaCl? NaCl. But what does this tell us? There's 1 sodium and 1 chlorine atom. So that means there's 2 atoms, 1 chlorine, 1 sodium, and sodium chloride, table salt. Now, what happens if you have more complex things? Well, let's look at an interesting one. This is sodium sulfate. And I could ask the question, how many atoms are in sodium sulfate? By the way, have you ever seen those little packets and things like electronics or optical equipment, like binoculars, telescopes, and everything, or electronics, and says, do not eat this? That's sodium sulfate because it absorbs moisture, water. And when you buy something like a new cell phone or a flash drive, and it's been sitting in a packaging for a while, you don't want water to get in there and do damage. And that's why they put sodium sulfate in those little packets that say do not eat. All right, now, how many atoms are in sodium sulfate? And I'm going to give you 15 seconds to do it. Go, go, come on. I'll give you a bonus 6. Time's up. Well, there's how many sodium? 2. How many sulfur? 1. How many oxygen? 4. Do my high level math. 7. Remember, this is the way I write a 7. So there'd be 7. Now, there's another thing I need to teach you, and that's called using parentheses. When there's more than one type of grouping, and we'll talk more about it, it's called polyatomic ions, we use parentheses. So, this is called calcium hydroxide. I believe this is also called lime, but don't quote me on that. And the question is, how many atoms are in calcium hydroxide? Well, here you have 1 calcium, but now we have these brackets, and you multiply everything inside the bracket times the number to the right and subscript of the bracket. So it'd be 2 times 1 oxygen plus 2 oxygen, 2 times 1 hydrogen plus 2, and therefore there are 5 atoms in calcium hydroxide. I can give you a hard one. Let's see if you're this is called magnesium bicarbonate. I don't even know if it exists. How many atoms are in magnesium bicarbonate? You have some? When you're done, give me a thumbs up. Or I guess now you can also do thumbs down. Thank you, Kayleen. I hope I'm pronouncing your name right. Thank you. I guess I am. Thank you, Jasmine. All right, let's try this. How many atoms are there? There's 1 magnesium. Now we have the bracket here, and notice the subscript is 2. It can be other numbers, but the ones I can think of off the top of my head up here, let's say this is the ones I come up with. And here we have what? Whatever is inside, you multiply by this number. So 1 hydrogen times 2 is 2. 1 carbon times 2 is 2, because you multiply by the number outside the bracket. Ooh, look, we've got 3 oxygen, but we have the bracket and then subscript 2. So 2 times 3 is 6. And if I do my math correctly, if not, someone let me know, that's 11. So there'd be 11 atoms in magnesium bicarbonate. And again, what's ever in the bracket, you multiply by the number to the right and subscript of the bracket. And that's why 1 times 2 is 2 hydrogen, 1 times 2, 2 carbon, and then 3 times 2, 6 oxygen. And this is how you deal with empirical formulas. Oh, let's try one more. This is sodium bicarbonate. You know it as baking powder. And we'll be using this later today in the lab, not baking powder, but another substance with sodium bicarbonate. So how many atoms are in sodium bicarbonate? And when you're done, give me a thumbs up. Thank you, Jasmine. Thank you, Kayleen. And Anna, is your thumbs up thing working? It is. Thank you. All right, let's do it. How many atoms? There's one sodium. There's one hydrogen. There's one carbon. Ooh, oxygen, you have the number 3. There's 3. So if I do the math correctly, 1 plus 1 plus 3, 3 plus 3, 6. And that's how you use empirical formulas. So here are 2 things I didn't cover, but you should know. When we're talking about mixture, there's homogeneous, the same throughout. That would be like the air you're breathing or the tea I'm drinking. Oh, is that good? I love my Republic of tea. And heterogeneous, not the same, like salad dressing, oil vinaigrette. Now, when we talk about formulas in chemistry, we're going to just deal in this class with the empirical formula, which shows atoms and how many. And water, H2O, there's 2 hydrogen, 1 oxygen, so 2 plus 1, 3 atoms. Sodium chloride, 1 plus 1, 2 atoms. And I did this. Now, when you have a bracket, whatever is inside the bracket, you multiply it by the number to the right subscript of the closing bracket. I guess you call it parenthesis. And here, how many in calcium hydroxide? 1 calcium, then 1 oxygen, no, times 2 is 2 oxygen. 1 hydrogen, no, times 2 is 2, so there's 5. And here we did a tough one, magnesium bicarbonate, 1 magnesium. 1 hydrogen, no, times 2 is 2. 1 carbon, no, times this 2 is 2. 3 oxygen, no, times 2, 2 times 3, 6, 11 atoms. And that's how you do it. Any questions? I do have my speaker on. Early on Zoom, I forgot to turn my speakers on. Right up here, you can't see them. I got 2, they're about this by this big amplified speakers for my computer. If you don't turn them on, they don't work. All right, let's move on. All right, let's go to this one. Everybody see chapter 3 practice problems on your screen? Thumbs up, people. Thank you, Jasmine. All right, with these practice problems, after test number 1, you'll understand why I call them practice problems. If you can answer these questions correctly, you will do good on test number 1, which I believe is coming up next week. I think so. I'll have to look at the schedule for tomorrow before tomorrow's class. Which means I've got to write it every semester, every class, I write new tests. All right, first one, what is, and notice it says only one of the 4 branches of chemistry. Well, I'm biased, organic is the best. Oh, I'm an organic chemist. There's inorganic, physical, analytical. I've only asked you to learn one. Organic, it's the best. Yep. And then this, for those who can't read cursive, what is matter? Anything that occupies space and has mass. Now, excuse me, what are the 3 states of matter? Remember, we went through this in class a couple of times. You should know they are solid, liquid, gas. I'm gonna look, oh, I got it right. So you should know the 3 states of matter. Now, when we talk about matter, there's pure substances and mixtures. I'll never ask you what's a definition of a pure substance or a mixture, but you should know examples. What would be examples of pure substances? Well, there are a lot. Water, gold, silver, oxygen gas, nitrogen gas, not air. Air is not a pure substance. And the list goes on and on. Now, name a mixture that you could purchase at your local grocery store. Well, you can get milk. At mine, if I go to, I think all of mine do, Jewel, they sell mouthwash, and it's a grocery store. Pop, remember Dr. White's from the Chicagoland area, and the stuff in a can or a bottle that's carbonated, non-alcoholic. We don't call soda, we call it pop. And mustard is a mixture. Now, if I didn't have grocery store, what would be another mixture? The air you're breathing. And that is a mixture because it contains nitrogen and oxygen gas. Now, each one of those alone is a pure substance, but when you put them together, mix them together, you have a mixture. Now, as I mentioned earlier, you should know what is homogeneous and heterogeneous mixture. Homogeneous, the same throughout. Heterogeneous, not the same throughout. And here I have, oh, I mentioned it earlier, oil vinaigrette. Remember, it separates into 2 layers, and that would be heterogeneous. Gasoline, well, I hope the gasoline I buy, I know it is homogeneous. Did I tell you the best gasoline out there? Did I talk about that? Do you guys remember? Thumbs up if you remember about the best gasoline to use for your car.
I just remember Shell, but what was the second one and the third one?
All right, I'll go through it again. I worked for a company that sold certain additives to all the petroleum companies, meaning gasoline companies. The best, and has been for decades, is Shell. Right below it and very close to it, almost identical, is Mobil. Marathon is a very good gasoline. The worst is BP, it used to be called Standard. I haven't been at a Standard station in decades because I know how bad it is. And I think I mentioned the story about 2 or 3, maybe 4 years ago in the Indiana, Gary, Indiana area, and also across the border by Gary in Illinois. BP, the refinery around there, shipped gasoline so bad it destroyed, listen to this, destroyed the car engines of about 3,000 cars that they had to pay to have replaced. No way am I ever going to put that in my car. By the way, I drive a Ford Explorer, have had them for a number of years. All right, remember, you should know the chemical symbols. So if I ask on a test, give the chemical symbol for carbon, C, chlorine, Cl, silver, Ag, gold, Au, oxygen, O, sodium, Na. I don't have that down there, but you should know things like K, potassium, Li, lithium, S, sulfur, and nitrogen. Now, I can also ask, give the name of the element with the following chemical symbol. Na, sodium, Br, bromine, C, carbon, Mg, magnesium, Au, gold, and my ring, and Ar, argon, and Kr, krypton. And by the way, unless I got kidnapped to another universe, in our universe, krypton is not a green solid at room temperature that kills Superman. It's a colorless gas. All right, next, I'm asking questions about physical property or chemical property. And a physical property is something you observe. A chemical property is something that tells you how that substance can change. And water freezes at 0 degrees C, that's a physical property. Oxygen is a gas at room temperature, physical property. Oh, I got the same one twice. Sorry about that. Iron can rust. That's a chemical property. Gasoline is flammable. That's a chemical property. How about water is non-flammable? Is that chemical or physical property? I'll let you think about it, then I'll tell you the answer. And the answer is water being non-flammable, they used to put out fires, the firemen do, is a chemical property. Now, a physical change is when a substance changes its state of matter. And what would be examples of a physical change? Well, if you boil water, water goes from a liquid. Have you ever seen steam on top, like in the winter? And that is water in a gas state, which we call steam. And that's a physical change. Or if you ever have an ice cube in a glass or anywhere else, and you look at it and come back an hour later, maybe longer, it will be all liquid. And ice melting is a physical change. Now, chemical changes, if you light a candle and it burns, the wax is undergoing a chemical change, giving off heat and two chemicals I'll talk about later in the semester. Now, let's get personal. I don't know if I told you this story or not. When I was about way down 2 or 3 years old, I can still remember this. My mother would tell me, because I just wolfed down my food. Wolf is an old expression. I don't know if they use it. I mean, just eat it as fast as you can. And my mother would say, chew your food before you swallow or you'll choke. Guess what? I found out she wasn't lying. Well, sometimes you got to do things the hard way to find out you shouldn't. Well, anyways, when you chew your food and swallow it, and it goes in your stomach, it's undergoing a chemical reaction. I don't teach that in this class, but when you take my organic chemistry, either 1212 at COD, or this semester I'm teaching it at Elgin Community College, it's called Chem 170, I do teach what chemical reactions, because that's organic chemistry, goes on in your stomach to break down the food. So when you digest food, your stomach is undergoing, your food is undergoing a chemical reaction. Now, I teach really in detail a number of things in my organic, but I hate to tell you this, but you're a walking chemical plant. Throughout your whole body, lots and lots of chemical reactions are happening. See, chemistry is everywhere. Now, I asked you to learn the definitions of what is a solid, liquid, and gas. And therefore, what's a solid? Well, it has definite shape and definite volume. So if I ask what state of matter has definite shape, definite volume, it's a solid. Now, what state of matter has indefinite shape, indefinite volume, and that's a gas. And finally, the third and final question of this part of chapter 3 problems, what state of matter has indefinite shape, indefinite shape, definite volume, and that's liquid. So you should know, hint, what state of matter has definite shape, definite volume? Solid. If you think about it, you got a solid. Does it change its shape? No. Does it get larger or smaller? No, it stays the same volume. That's a solid. Now, a gas can spread. If I were to if you were sitting in a room like mine, and I came in at the door and standing at the door, and I had a bunch of roses, I like roses, and other flowers too. In a little while, or if I opened up a bottle of perfume, you would smell that. That's because the gas from the flowers, what you smell, would have infinite volume, infinite shape, and fill the room, which is why it's nice to have flowers in the room, even though I don't have any in my office. I don't think I have it in my house, my backyard. But anyways, you should know the 3 states of matter and how to identify each state. All right, that part of the question, the practice problems. Anybody have any questions? I'm all ears, literally. That's one of the sad things in life, not sad, your ears keep on growing. All right, let's move on to the other chapter 3 practice problems, and that's dealing with temperature. Now, let me remind you that the formulas for converting temperature from one to another will be given to you. Let's hold on while I open it up. That's interesting. I don't have it here. All right, where did I hide it? All right. All right, if you go to course information, go to lectures, everybody can see Blackboard, and you scroll all the way at the bottom, almost, and you'll see important information, test number 1. If you click on that, you'll see, everybody see the 3 formulas on your screen? Give me a thumbs up if you can. Oops. You should. Everybody see that on your screen? Important information. Thank you, Jasmine. These will be given to you. You do not have to memorize them. Years ago when I taught 12, and even years ago when I taught 1105, I would have the students and most instructors memorize this, I've come to the conclusion, I'd rather you show me you know how to use these than how good your memory is. So let's look at the following. Remember, this will be on the last page. You're welcome. This will be on the last page of the test number 1. And test 2 and 3 and 4 and the final, I have different important information because there are other formulas that you don't have to memorize. All right, let's go back to the problem set. Now, this is called the word problem. Relax, and you have to read it first. If the temperature of a liquid is 134 degrees C, what is the temperature of the liquid in degrees F, Fahrenheit? Now, one of the things, I don't know when I developed this, somewhere in college I did, when I'd have a word problem, relax, they're easy to do once you do the following. Once you've read it, first of all, put down what units, what are you being asked to find? And I've somehow developed, start with a question mark and then put what we're trying to find, degrees F. Underneath it, I put, what are we given? Well, we're given 134 degrees C. Therefore, I want to convert from centigrade to Fahrenheit. And here's the formula that will let you do it. Now, this you don't have to memorize. It's given to you, but you do have to know when to use it. Now, I put in the 134 and do the multiplication and then add 32. Now, on test 1, it will say underneath your name, please use proper significant figures for all calculated answers. Underneath your name, it will say, please use proper significant figures for all calculated answers. Now, if we look at this formula, 1.8 and 32 are exact numbers because they're part of the definition or this formula. Again, 1.8 and 32 are exact numbers. So the only number you have that's significant is degrees C. So whatever, how many significant figures that is, that should be your answer. Therefore, how many? All non-zero numbers are significant. Says 3 significant figures. Our answer should be 3 significant figures. Now, I didn't do this, but I'll do it now. Now, my calculator gave me 273.2. And here's it in scientific, which is I got it set up. And this is 4 significant. So you have to round it off. Everybody see my whiteboard? Thumbs up, people. Maybe not. Thank you, Kayleen. All right, so you have to round this off to 3 significant figures. Keep the 2, keep the 7, keep the 3. Use that to round off. That's 4 or less. I'll drop it. This becomes 273. Here, keep 2, keep the 7, keep the 3. Use 2 to drop off. And that becomes 2.7310 squared. They're the same number. This is how you write it in scientific notation. So don't forget, your calculator will give you all these really long numbers sometimes. And on my tests, and real world too, you have to know how to round it off And for the temperature formulas, the temperature you put in is the number of significant figures you get as an answer. All right, let's do another one. If the outside temperature is 24.5 degrees C, what's temperature in degrees F? Well, it's the same thing, 3 significant figures, I rounded off. All right, let's do a different one. Number 3. If your oven temperature is 353.5, what is your oven temperature in degrees C? Celsius. And again, when you read a problem, what I do, and it's helped my students over the years do well on my test, and also in other classes. Back, one student came to me after my class was done, and right after the final, she came up to me and said, boy, I wish I learned how to do this, how you teach word problems before I took math. I would have done a lot better. I guess they have a lot of word problems in math. I know they do. I've taken math classes. So what are we being asked to find? Degrees C, and I put that question mark. You have to do this? No, but the more you let the paper do your thinking, put things down, the better score you get on a test. Has happened to me personally, has happened to my students. And what are we given? Degrees F, 353.5. Now we're trying to go from degrees F to degrees C. Important information. You have degrees F, you want to go to degrees C. Here's the formula. Degrees C equals degrees F minus 32 divided by 1.8. Remember, 32 and 1.8 are both exact numbers. The only number that you use to determine how many significant figures in your answer is degrees F. So we put it in there. Here's a common mistake students make with this formula. You do the subtraction before the division. I'll say it again. Common mistake students make. You do the subtraction before the division. So I'll subtract that, divide by 1.8. My calculator gives me a much larger number, but notice 353.5 is 4 significant figures. I round the number that my calculator gives me to 4 significant figures. And I just looked at my clock. It's time for a 5-minute break. Let's take a 5-minute break. I'll see you in 5. I can get up and stretch. Time to get going. All right, we're doing chapter 3, problem set for temperature. Let's finish it up. And let's look at number 5. And hopefully everybody, can you see number 5 on your screen? Give me a thumbs up. Thank you, Caitlin. All right, thank you, Jasmine. All right, now, temperature of gas is 303 degrees C. What is the temperature in Kelvin? K is Kelvin. It's not a referential degrees. It's an exact or absolute. That's a better term. And therefore, that's why we don't have the degree symbol. So what are we trying to find? K is Kelvin, temperature in Kelvin. We're given it in Celsius or centigrade, Celsius. The old name is centigrade. I still like that better. But anyways, and the formula, how do you go from centigrade to Kelvin? Kelvin equals degrees C plus 273. 273 is an exact number. Remember, you're adding, so you'll have the same number of significant figures to the right of the decimal as the number that has the fewest to the right of the decimal. Well, in this case, 303 has none. Therefore, 303 plus 273, here's the number. Now here, I tricked you. I have, if the temperature of a liquid is 101.5 degrees C, then what is the temperature of the liquid in Kelvin? Well, you're asked to find question mark Kelvin. You're given this number degrees C. Here's the formula you use. Remember, you don't have to memorize it. I will give that to you. And now, remember, 273 is an exact number. So I have 101.5 plus 273. Notice we have one significant figure to the right of the decimal. Our answer should have one significant figure to the right of the decimal. I like my special effects. And it's Bad Humor Tuesday. And that's how you do it. Now, if we look here at the formulas, notice from going from Kelvin to Fahrenheit, you first have to convert it to centigrade and then centigrade to, or Celsius to Fahrenheit. Guess what? In all my chemical career, I've never had to do that. Never. And it's the only time I've seen people do that is when instructors, not Dr. White, will put that on a test. If temperature is 25.7 degrees Kelvin, what is it in degrees F? Fahrenheit. And that's not real. I've never seen it done in the real world. Therefore, I will never do that. All you have to know is how to use each one of these formulas alone. I'll say that again. Dr. White lives and works in the real world and still does. And therefore, you only have to know how to use each one of these formulas alone. The first one right here converts Celsius to Fahrenheit. The second one converts Fahrenheit to Celsius. And the last one converts Celsius to Kelvin. In fact, I've never even gone the other way. Kelvin to Celsius is down. Why? Because I've never seen a temperature measuring device known as a thermometer in Kelvin. It's either Fahrenheit or centigrade. All right, any questions about chapter 3 problem set? because of our shortened week, next Monday, I will go through chapter 4. Oops, I gotta fix that finger someday. Chapter 4, problem set. Next Monday, I'll go through chapter 4, problem set. Remember, if you can do the problem sets correctly, you'll do good on my test.
So I just have one more question. So if you want to take the test next week, we have to just drive to the school and just show up, or we need appointment or something?
All right, that's a good question. Now, to take the testing center, a test at the testing center, which is at the main campus in Glen Ellen, and they're open Monday through Thursday. They're not open Friday. I'm not sure what their hours are. I think they start at 8:30 or 9. Maybe I'm wrong. You should look. Hold on. All right, everybody see the academic testing hours?
Yeah.
All right. First of all, we're in August through December. So they're open. The first column is Glen Ellen. On Monday, Tuesday, I'm glad I checked, from 11 in the morning until 7 p.m. And then on Wednesday and Thursday from 9 a.m. to 5 p.m. All right, next week, assuming next week is a test, you can go in there anytime, Monday, Tuesday, Wednesday, or Thursday, when they're open to take the test. Now, I give students, normally I give an hour, because you're in the testing center, I think I give an hour and 15 minutes or an hour and a half. But don't show up at 5 p.m. when they're closing. If you're going to take the test and need an hour, be there by 4. If you come there earlier, you won't have that problem. Now, here's the way it will work. This weekend, or probably Friday or Saturday, probably Saturday because they're not open Friday, there's a form for faculty to fill in the names, and they actually have one where I just put in the course and then upload my test, and I'll do a periodic table. When you come there, they'll have printed out for you. You get to take it and you give it back to them. You need a photo ID, and I'd highly recommend bring your calculator. Don't use one of theirs, because you'll know how to use your calculator. Hopefully you practice it. If you're not sure how to use your calculator, come to my office hours. Remember, today's Tuesday, so my office hours tomorrow on Wednesday. And anybody who'd like to see different office hours on Monday and Wednesday, email me and I'll see if I can change them. If enough people want to change. Now, you'll go there. The way in the past, net under COVID, I do it online. And there's a way of doing that. Because COVID is, the governor's COVID policy has changed, so campus is open. For the net course I'm teaching now, the chem department decided that all the tests and the final have to be given at the main campus. Since it's a net, everybody has different schedules. That's why we're using the testing center. So how do you take the test next week? Monday through Thursday. You go to the testing center, bring your calculator. I bring a writing a couple of pencils. You can use pen. I'd use pencils, and bring a good eraser, and then your calculator. Take the test, and next, the Saturday after the test is given, I will go to the test center, pick them up. I'll grade them. Now, one of the things I worked out when we're doing everything online is I'll be able to send each person an individual email with your points for each question. And the following Monday after a test, I will go through the whole test. Now, you won't have your test in your hand, but what I will do is I'll email out a copy, a blank copy, and the following tests we give that Saturday, when I go pick up the test, I will stay a little while by the library. And if you want to pick up your own test that you had actually written on, I'll have them with me from the previous test. And I'll do this for the first 4 tests. Test 5 in the final, I never hand back. That's just a policy I have, but you will get the points. All right, does that help, Anna?
Yes, thank you.
You're welcome. And don't forget, for Anna and everybody else, I mentioned earlier, but I'll put it again. Test number 1 review is no longer in cursive. It's typed out so you can read it if you can't read cursive. That's so sad they stopped doing that in school. And in my personal opinion, so stupid. But that's my personal opinion. Let me close this. Let me do this. Let me go here so you can see it. I'm gonna, who asked, Kayleen asked lab time. What we're gonna do, I'm gonna do about 20 minutes of lecture, because I lost some time yesterday. I think we're ahead, but I still like to do about 20 minutes of lecture. Then at 10:30, we'll have our first lab. You're actually working with stuff. Ooh, okay? Thank you, Kayleen. All right, everybody see the Bohr model screen on your screen? Thank you, Jasmine. All right, last week I had ended up, hopefully you all had a nice Labor Day weekend. I did. I got a lot done around my house and everything because of some dental surgery I had on Thursday. I didn't make any plans to go anywhere because I was healing up. As you can tell, I'm back to normal, almost whatever normal is. But anyways, we're talking about where are the electrons? Remember, in an atom, the nucleus, the center of the atom, has the protons and the neutrons. Remember, what I'm talking about right now is test 2, not test 1 material. And usually I'll finish up a material on a test before the test, and then I'll continue on with new material, but this gives us time to do the practice problems. All right, so when we talk about where are the electrons, if in the center there are the protons and neutrons in the nucleus, all around that are the electrons. Now, Bohr, Dr. Bohr, German chemist, came up with the first concept of that, and that the electrons travel around the nucleus at fixed distance. By the way, click, the switch, will this be on a test, is in the off position. Now, these orbits, Bohr orbits, had specific numbers, and they call them quantum numbers. And there's different distance and energy. And the energy between each orbit is fixed, and that's called the quantum of energy. And electrons going from higher orbit to lower orbit give off energy in the way of light, photons? Good question. Fixed distance. Here's this finger, here's this finger, the distance between it, let's say it's 8 inches, it always stays that. If it went like this is no longer a fixed distance. It's always like this, it's a fixed distance. Does that help, Kayleen? Thank you. By the way, all questions are good questions. Thank you for your question. And I really practice and mean that. There's no such thing as a dumb question in my class or in my world or in my universe. All right. And you can measure the energy between the different orbits by measuring the type of light given off, energy of the light. And chemists did that. And that's how fireworks go off. What happens is, if you've ever seen fireworks, which Dr. White loves fireworks, it's chemistry at its best, at least one area. When the explosion happens, that gives off a lot of heat. And there's certain elements, actually I'll call cations, I'll teach you about this later, that go to a higher orbit. And when they get away from the explosion, all of a sudden, what am I doing up here? And the energy that forced it to a higher orbit or distance from the nucleus is gone. So it goes back to where it was, and it gives off light. And different cations have different orbits and give off different light. By the way, this is my favorite color. I love fireworks with a lot of red in it. And whenever you see a fireworks show, you're seeing a demonstration of what we call quantum mechanics. Quantum mechanics is a branch of physical chemistry dealing with where are the electrons. And it's probably, for me, one of the second most hardest things in chemistry I had to learn. Now, these energy levels, and again, switches off, remember I showed you the atomic spectra, are associated with the lines in there. And different quantum numbers are numbered very cleverly, 1, 2, and 3, and so on. Click, switch is still off. And these levels are called shells. The quantum levels are called shells. Now, I already mentioned this, but where are the electrons, protons, and neutrons? Click, the switch is on. If it was a dial that I could turn to 10, I've just turned it to 20. I stole that from the movie, This is Spinal Tap. But anyways, the nucleus, very dense, positively charged center. I don't have here, but I should have. That contains the protons and neutrons, or neutrons and protons. And all around it, really spread out, which is why we call it a cloud, are the electrons. And that's the volume occupied by the electrons of an atom. So you should know, hint, hold on. Don't you love it when I'm subtle? You should know this and this. The nucleus is the center of the atom, containing the protons and neutrons, and around it are the electrons in the electron cloud. And this, I'm going to turn the switch off, but if the nucleus was the size of a baseball, then the atom would have a diameter of 2.5 miles. That means the electron cloud goes from the center 1.25 miles one way and 1 mile the other, quarter the other. The nucleus is really dense and the electrons are really spread out. All right, switch is on. I won't ask definitions, but you should understand what these are. When we talk about where are the electrons are in the electron shells. And the electron shells are the region of space around a nucleus that contains electrons that have, this is important, approximately the same energy and spend their time, most of the time, approximately, not exactly, approximately the same distance from the nucleus. So we have these shells, like an egg has a shell around the yolk. Did you get that, yolk? Oh, I am sorry. That was the worst joke. Remind me, never use that again. But anyways, the electron shell is the area where you find electrons that have approximately the same energy and spend their time. And a key thing is, again, approximately the same distance from the nucleus. Remember, nucleus center of the atom. Now, each shell has subshells. Remember, sub underneath, like submarine, like subatomic particles. Well, electronic subshells are in the shell, electron shells. And a subshell, electronic subshell, time out for a water break, is the region of space which an electron within an electron shell that contains electrons that have the same energy. I didn't put it there, but also have the same distance from the nucleus. I will never ask on a test what's an electron shell and what's an electron subshell. So we have these shells, certain distance from the nucleus, and the shell, think of it being thick, not real thin. You have subshells where you have electrons that have the same energy and the exact same distance from the nucleus. Now, when we talk about shells, we also have the concept of orbitals. And orbitals is a region in an atom where the highest probability of finding an electron. We have in the center of the nucleus. And I won't ask you ever what's an orbital, but if Dr. White was all powerful, I'm not, but if I was, I could stop all motion in our world, in our universe, by doing that or pushing a button. I can't. Even the electrons which are moving around the nucleus would stop. And the orbital is the shape around the nucleus where you'd have the highest probability in that area of finding the electrons. Now, orbitals play an important role in our life, which I don't teach in this class, but they govern the shapes of molecules in our universe, especially in our body. Like the orbitals are responsible for the shape of your DNA. Yep. And how many of you ever heard of the fact that trans fats are bad for you? Anybody heard that? Give me a thumbs up if you've heard trans fats are bad for you, unhealthy. I see one person has, and that's due, you can trace to the shape of certain types of orbitals. Yep. So is this stuff important? Yeah, it plays a role in our daily life. Now, switches on. However, you don't have to memorize this table. You do know have to know how to use this, because I will give you this table, important information, test number 2. In the past, I made students memorize this. Now, the electron shells have very complicated names. The first shell is called shell 1. Ooh, what about the second shell? It's shell 2. What about the third shell? Shell 3. And the fourth, shell 4. And for this class, that's all you got to know. Now, important thing I don't have here, but you should know. The energy goes from lowest to highest, from top to bottom in this chart. The energy associated with that shell, 1 is the lowest, 4 is the highest. And as you go down, you increase your energy as you go down this table. And this you should know. So shell 1 is the least lowest energy shell in an atom. Shell 4 is the highest. 2 is greater than 1, but less than 3 and 4. 3 has more energy than 1 and 2, but less than 4, and 4 has the highest. Now, as I mentioned, each shell has subshells. Now it gets really complex. Shell 1 has 1 subshell. Shell 2 has 2 subshells. Shell 3 has 3 subshells, and shell 4 has 4 subshells. Boy, this is thirsty work. So we have shells and subshells, and the shell, electronic shell, is the approximate distance from the nucleus that electrons have approximately the same energy and approximately the same distance. Now, each shell has subshells, and this chart teaches you that shell 1 has 1 subshell, shell 2, 2 subshells, 3, 3, and so on. Now, when we come to subshells, they have names too. And they're also known as orbitals. And those are S, P, D, and F. And these are the orbitals, also known as and they're known by letters, not numbers, S, P, D, and F. Now, again, going this way, S is the lowest, F is the highest energy. And another way of putting it, does everybody know the symbol from math, less than, right here? That means S has less energy than P has less energy than D, thank you, Jasmine, and F has less energy than, or D has less energy than F. And this is the lowest to highest, and this you should know. We're talking about energy of the electron. Now, I will never ask on a test, but a number of years ago, a student asked me, where did they get those letters S, P, D, and F? Why didn't they just take A, B, C, and D? Well, they came from atomic spectra back around the late 1900s, 1800s, early 1900s, that when they're looking at trying to figure out where are the electrons, and this isn't that old. This is a little over 100 years ago, they started figuring this out, which in the history of mankind, 100 years ago is not much at all. But they looked at atomic spectra and somebody came up with certain lines are sharp, others are called principal, others are called diffuse, and some are just fundamental. How they came up with that, Dr. White is not a physical chemist and hasn't been worked that much with atomic spectra. I did undergrad to learn it, but other than having certain trace metals, organic chemistry doesn't use atomic spectra. We use other things. But anyways, these are the subshells, S, P, D, and F. Now, in the past, students would have to memorize this chart. The number of electrons in each orbital, and chemists found out that S can only take 2 electrons, P, the maximum you can put in there, 6, D, 10, F, 14. And as I mentioned earlier, just like the previous chart with shells, the subshells, S is the lowest energy, F is the highest energy. And that's how the subshells go. Again, I used to make students memorize this, but this will be given test 2 important information, but I won't put the energy lowest to highest, but I will give you orbital subshell number of electrons S2, P6, D10, F14. How that happened? That's just the way Mother Nature did. Now, if I look at the clock, I think this is a good time to stop the lecture. Don't leave yet. And it's time for lab. It's lab time. First of all, I got to go open my lab. All right, everybody see Blackboard on your screen right now? All right, now, if you click on assignments, and I'm in student view, so this is how you'd see it. You just wouldn't see this on the top where it says student preview is on, that I have, you don't. But I'm in student view, which is how you'd see it. Click on assignments, and don't forget to hand in this contract, and please read the safety manual before the parts on chemistry, before you do this lab. Now, if you notice, right after COD at-home safety contract, fall 2020, if you scroll down, it'll be lab 2, scientific method, I have no idea what ADA stands for, the number. But anyways, I have both the PDF file of the scientific method, what you're going to be doing, and I'll be going through that, and the lab report. Now, I also have instructions for making a PDF file. And if you don't have a scanner, there's a free app. Don't spend money on the expensive, spend money, or what do they call that? The expensive app. Just use the free version as opposed to the paid version. And Cam Scammer will help you. And I think most of you already did that with lab number 1. Don't forget today, lab number 1 is due. Now, I'm going to go through the scientific method, what you're going to do, and also what you're going to have to write up. But before I do that, if you go to your lab kit, which hopefully you all have, you should have a package and says chemical safety set. Now in there, you have a pair of goggles, gloves, and an apron. Now, when we're face to face, COD gives faculty better goggles, and you should wear these during the lab. They protect your eyes. I have my goggles. Actually, this set, these are actually a good pair of goggles. I've seen a lot cheaper. These are pretty good. Now, the other thing they give you that you should wear, just to be safe, is an apron, which is not that bad. Now, they give you 3 of these ties. One goes on the top right here. You tie it off. Then on each side of the apron, you have a hole here that you can tie off one of these, it looks like monster shoelaces, and therefore you can put this on. I don't have it adjusted. You can tie it off and you're protected. Don't want to ruin my fine hairdo. But anyways, you should wear this seriously. You should wear your safety goggles for every lab, and also you should wear gloves. When we're face to face in a lab at COD, everybody in the lab has safety goggles. I do, you do, and then we also have gloves. We provide them for the students. These gloves look thick enough. At the end of today's lab, rinse with water, and then you can take them off and save them for next lab. So what's today's lab? Good question. Thank you. Today's lab, which they name Faster Plop, Plop, Fizz, Fizz, a scientific method investigation. The title is a generation gap. What do I mean by that? How many of you have ever seen an Alka-Seltzer commercial? Give me a thumbs up. Well, I see one person, and they used to, the Alka-Seltzer, they'd always have the jingle, plop, plop, fizz, fizz. Oh, what a relief that is. Dr. White's been brainwashed by commercials. And what this lab is going to teach you is about the scientific method. And the scientific method is, how do scientists do things? Come up with ideas. How do we understand things that are happening in our daily life, in our world? And that's what chemists do, also other scientists. And the scientific method is a way of coming up with understanding, investigating things that happen, and that, what does this mean? And when you use it, outcomes, what happens, what can you derive from that? you formulate a hypothesis, then you test it empirically. In other words, get data, observe something, and this data helps you understand dependent and independent and controlled variables. Now, in here, they talk about controlled variables. I'll be very honest, I've never used that word. I've always stuck with this independent and dependent. Now, very important thing I should mention right now, which means I'll go back to full screen. Anything we do in the labs will never be on my test. I'll say that again in slow motion. Anything we do in the lab will never, ever, ever be on a test. But you do hate to do it to do the lab reports. Thank you, Jasmine. I keep them separate. That makes the labs more enjoyable. You're welcome, Anna. And that's just my own personal policy, because labs should be fun. And the labs they have here look like they're, considering you have to do it at home, are enjoyable. All right, let's get back to the lab. That's not what I want. All right, so they give you certain important things, and here you should wear your goggles, your gloves, and an apron. Now, they ask you to submit a photograph. If you can, I'd like you need a stopwatch, which if you don't have one, use the old method, 1001, 1002, and so on. But I think most of you have stopwatches on your cell phone that you can use. I'll let you read the background in here. You can do that on your own. And a hypothesis scientific use experiments or design experiment, that's called DOE, design of experiments, to test a hypothesis. And again, make an observation, ask a question, develop a hypothesis, design an experiment, run an experiment to collect data, analyze the data. Is your hypothesis supported or not? And if it isn't, you reverse the hypothesis. Now, what they don't show here is if you find something that based on your data, your hypothesis is always true, we call that a law. A law is something that's always true in chemistry. We're different from the law in our society, like you shouldn't rob banks because that's called stealing or theft. That's law in our society. But in science, especially chemistry, a law is something that's always true and based on experimental results of a hypothesis, it's always true. Now, what would be something you might want to consider testing? Well, look at it. Here's water in this bottle. If it's at this temperature, it's a liquid. If I put it in my freezer and come back the next day, it won't be a liquid. It's a solid. So what's behind that? And you could say, well, I could put it in a different container or in a cooler where the temperature is a little warmer than my freezer, and it froze again. And eventually I'd find that if the temperature is above 0 degrees C, water is a liquid. If it's 0 degrees C or lower, it's a solid. And I come up with what's called the freezing point of water or melting point. Either way, it's the same thing. And that's how you do it. Now in this lab, let's look at, wrong thing again. There we go. Now, there are different variables when you look at something or run an experiment. A variable is something you can change or does change. And they don't show here or tell here, but one of the most important things in science, especially chemistry, and this is something when I was in the chemical industry and I still consult, a lot of chemists forget about and get into trouble getting wrong answers is when you do an experiment, you only change one variable at a time. When you do an experiment, you only change one variable at a time and you measure other variables. And you have an independent variable as a factor hypothesized to produce the effect under investigation, and then dependent ones that are measured. Now they have ones that are controlled that I've never used that are all other non-independent or non-dependent variables. I've never used that. And they give some examples of how to observe something, come up with a hypothesis, and then test it. I'll let you read that on your own. Now, when it comes to today's lab, hold on while I get it out. All right, first of all, there's a package or bag in your box that says Principles of Chemistry Equipment Set. And what you will find in there is, and be careful with this, the thermometer. You'll need 3 of these cups. In the same container, you have a plastic beaker that you can use for measuring. And you also have, if you don't have one at home, a grease pencil. Now, the grease pencil, I'm not going to do it. You can mark the cups with the letters they'll tell you. Now, you'll also need, from your box, you can find this. It's a little plastic bag that has Alka-Seltzer. And on the label here, it says, faster plop, plop, fizz, fizz, semicolon, a scientific method investigation. Now, let's talk about something before we go into the actual lab. When you're using a measuring device, and look out, artwork from Dr. White, don't laugh too hard. You have different lines for the height of things. When you put water in, the level will not be straight across. Water forms a meniscus. It's like a U. And here, if I were to fill it up to here, even though the water level would be up here, you measure the bottom of the meniscus, the U, when you're measuring. Now here, you're supposed to, in each cup, put 200 milliliters of water. And you can use your tap water. In the labs, we use deionized water, but for this lab, tap water. Now, maybe, I don't know if you can see it, as 200 milliliters. And for this one, you don't have to be exact and spend the next 20 minutes trying to get exactly 200. But for each one, you're going to be putting in each cup, 200 milliliters of water. Now, the first one, take some water and either turn your tap on cold and let it run for a while, or in another container, not this, put some water and some ice cubes and let it sit for about 5 minutes, and then pour just the water, not the ice cubes, in here, cold water, and you'll measure 200 milliliters. And you'll put it in one of these cups, measured C, cold. Next, take some water that, here is your thermometer. Now, this comes out, actually, this is a nicer one. I haven't calibrated and see how accurate it is. Thermometer. Now, this right here keeps your thermometer from rolling off the floor and breaking. Now, here we have a thermometer that measures degrees C, Celsius. And I think you all know how to read a thermometer. Now, important thing, these thermometers, do not shake it down. Do not do this like a medical thermometer, the old glass ones. This one, all you gotta do is put it in there and let it record the temperature. And you look at that. Now, these thermometers, you should be able to get 3 significant figures. If you look hard enough, hold on, I'm gonna cheat. Yep, you can get 3 significant figures. Now, let's look at how to read a thermometer. What's temperature in my room office right now? It's 26.5. Now, here we have, you'll see the larger numbers, 20, 30, 40, and so on. In between, you'll see a mark that's 0.5. So if we're exactly there, it'd be 25. If it was right exactly this red line lined up to that, it would be 25.0. 3 significant figures. Now, if you look here, you'll see in between the 20 and 30, there are 10 lines counting this unnumbered larger line at 5. And therefore, you can measure 30, 21, 22. Now, how do you get 3 significant figures? Now, when you're using this, make sure this stays on, because if you put it on a surface, a flat surface, hold on. That stops it from rolling. And if you don't have one of these on there, I always tell students, because not all ours in the lab at the school have them, you always put this on a paper towel or 2. Stop it from rolling off the floor, but you've got this on there. Now, when you look at a thermometer, and I'm going to be going an extra 10 or 12 minutes, then we'll be done. But here's our thermometer. And you have, this is a alcohol thermometer, and you have that red line here, the liquid. Now let's blow it up. Let's blow up the area in the thermometer between 20 and 30. If the red line goes here, this is 21, 22, 23, 24, and this is 25. Notice it's not exactly on this line, and it's not exactly on there. And what I'd like you to do, if this top of this red is not exactly lined up with here or here, but in between, you call that 0.5. So this would be 24.5. If it was exactly lined up with this 24, then it would be 24.0. If it was exactly lined up with 25, it would be 25.0. So you should be able to either record, is it 24.0 or 24.5, three significant figures. Now, today's lab, you're going to be observing and measuring the time of what affects this dissolving of a tablet of Alka-Seltzer in a glass of water. And the variables you're going to use if I can spell it. One is temperature. And this you're going to change. And the other is time to dissolve. And this you're going to measure with your stopwatch. Now, they ask you to graph this, and I'm not going to have you graph. I think I have it as a question. I see a question. Nope, not a question. All right. So what are you going to do in this lab? Let's take a look.
So we are doing just your things that we need to fill, or we have to do theirs?
Say that again, Anna.
Because I saw that you posted like a Word document, and it also
You can fill either one. I'll show you how to record everything and what you have to submit after I go through what you're going to do. Okay?
Okay.
And if not, ask questions, which you're getting the hang of, which is a good thing. Now, you'll need the Alka-Seltzer. Now, you'll use 5 of these. I'm going to modify this. You'll only need 3. You'll need your beaker, your thermometer, the pencil, wax or grease pencil, I call it. And they have 6 cups. You can use 3 cups because you can rinse them out in between each run. And don't forget safety. Now, what you're going to do is label the 3 cups, one C for cold, one H for hot, and one RT for room temperature. And you'll use, they call it a wax pencil, I call it a grease pencil, on your cups. Then you'll have a timing device, way to measure. You'll make an ice bath with some water and ice in a bowl or cup separate. Open the Alka-Seltzer. Now here carefully, don't cut yourself. Remember, you should have gloves on. You'll take a scissors or knife and score it in the middle. You'll have the tablet and put a line. A couple of times run the knife or the part of a scissors. Dr. White has nice scissors for in my hobby room. And you'll just run it. Be careful you don't cut yourself. And then you'll break it. Now, you'll need 6 halves. So that means you'll only need 3 half tablets. I'm changing things. Now, in another beaker, use the 250 milliliter beaker and measure out tap water and use like 50-50. Now, if you want to be exact, you can measure the water coming out of your tap and should be about 25 degrees C. By definition, room temperature, you're a little above or below, that's okay. And you'll measure 200 milliliters and you'll put it in the cup, measure or got RT on it. And finally, you'll turn your tap water to hot. When it gets nice and hot, you'll put 200 milliliters in the speaker and put that into a separate cup called H. Now, here's the experiment. Start with the cold one and put the half a tablet in there. And it's going to go making bubbles and everything. When it's total, start when you drop the tablet in there, start your stopwatch. And when it's all stopped fizzling, and you can't see any solid in there, then you stop it and record that time. And then there's a table here where temperature, and you'll also, before you do that, put your thermometer into the cup of cold water. No ice cubes should be in there, and you measure the temperature. Then you'll put the tablet in there, measure the time until it all dissolves. It's all gone. In the cup with the room temperature water, you'll put the thermometer in there and measure the temperature. Then you'll put half a tablet and you'll measure the time until it's all dissolved. It's all gone. The bubbles stop. You see no solid. And finally, the third one, you'll put with the hot water, you'll put the thermometer in there, measure the temperature, and then put the half a tablet in there and measure the time it takes for it all to dissolve. And you'll record it here. Now, when you do certain reactions or experiments in the lab, you always do things at least in duplicate, sometimes a lot more if it's really important. And in this lab, they have you do it in triplicate 3 times. Nah, you don't have to. Let's just do it in duplicate. And what you'll do is repeat the same thing. In the cup, thank you, Jasmine. Again, Dr. White's worked in the real world, so I know real world stuff. And the one thing, I don't like wasting time if I don't have to. But at the same time, I want to do everything right. Now, you'll repeat it again. Fill the 3 cups you did, dump them down your sink. Nothing's hazardous. Don't forget, you should have your safety goggles and gloves on. And don't forget, if you need to, wear an apron. But for this lab, well, you should every lab wear an apron. But anyways, but you should have your goggles on and your gloves on. You'll dump this down. And once again, you'll take some water, put some ice cubes in it, let it sit for a while. Fill it, then put that ice water, just the water, in the cup labeled C. You'll take some room temperature water, 25 degrees C, adjust your hot and cold to get that. Put that 200 milliliters. Remember, use this 200 milliliters. We're not changing the amount of water. That's kept the same. The temperatures are different, and that's our variable. And finally, the hot water, and you'll put the tablet in there, cold water. You'll measure the temperature, put the tablet in there, measure how long it takes for you to, for it to dissolve. So you'll do that twice for each temperature. All right. Let me make sure you should see. Everybody see the PDF file that I opened up? I think I also have it as a Word file. Thank you. Put your name, put the date. You really don't need the date. Now, in here, activity 1, state a hypothesis, and that deals with temperature, water, and how fast it dissolves. Here's your data, but for run 3, leave that blank. Now it says average. Take the time for the temperature, this one and this one, add them, divide by 2. The time, this time and this time for the cold, add them together and divide by 2. Do that for room temperature and also hot water. I didn't mention earlier, but observations. Do you see bubbles? Now I have here using graph. Why don't you, let's do the graph. Now, the question is, how do you set up a graph? You don't know how to use Excel, or you can use manual. I did put in the lab for today. Carolina company has a nice thing how to graph, or come to my office hour. Now, what's on the X and what's on the Y? Well, don't tell anybody I'm helping you out. Whatever you're actually controlling, temperature goes on X, and what you're measuring goes on Y. What you're controlling, temperature, X, what you're measuring, time, Y. And what are the 2 variables that you graph? Because those are the variables you measure. And what's the independent? X. What's the dependent? Y. All right. Now you can use your graph to do this. Now I added a few of Dr. White questions. Number 7, how would you make the Alka-Seltzer tablet dissolve quicker in water? What would happen to the rate of the Alka-Seltzer? You dissolved it, and you put, when you're going to dissolve it, you put it in a freezer when you're about to dissolve it. And hopefully you all know freezer is very cold. And what data helped you answer this question? Now, I have this both as a PDF file, and also I believe I have it as a Word document. You can write either one, type in your information. Now, you should be able to, in the both documents, import an Excel spreadsheet to put in too. If you have problems, let me know. I can help you out.
Can you show us how to do this graph in Excel?
How to do what?
How to do the graph in the Excel?
I'll tell you what, a better way, can you come to my office hours?
Well, I'm at work at the time, so I'm
All right,
not
I'll tell you what. Tomorrow, beginning of class, I'll show you how. What I don't have and I don't want to do on the fly is set up a spreadsheet with numbers in it, okay?
Okay.
I'll show you how tomorrow. Speaking of which, time to put a Post-it on my everybody see that? That goes in my mirror in my bathroom. That's why I put important things. Shh, it's a secret. But anyways, I'll do that. Now, when you're done, you can rinse these out and dry them and maybe use them again. Everything, all liquids go down your drain. Now, here's an important thing. Anytime you do an experiment, even with gloves, even though it's not dangerous, I still do this as a chemist. Always wash your hands with soap and water when you're done with a lab. And that's just a safe thing. You can always tell a chemist, especially organic chemists in a restroom in a lab building, they always wash their hands before and after they use the restroom, because you don't want chemicals where you don't want chemicals. I have a story about that, but I won't tell it today. Now, don't forget, when you're done, thermometer, which I'm not sure yet, but we probably might be using it, put it back in this nice container. It's really nice. They did a nice job. And don't forget, keep your safety goggles and gloves. You can let your gloves dry out. The lab is due a week from today. You have any questions how to do a lab or how to write up a lab? Remember, what's my policy about questions? There's no such thing as a dumb question. So you can either come to me during my office hours or ask after a lecture or a lab, okay? And with that, I went a little longer than I thought, but we got a lot done this morning. With that, I'm done. And I'm gonna say, Gang gesund, which, thanks you, Kayleen, which means go in health in Yiddish. Yiddish is a mixture of German and Hebrew. And my grandmother used to always say that when I'd leave her. What a great woman she was. So I'm gonna say to you, Gang gesund, goodbye. I stole that from Beverly Hillbilly's granny. Goodbye.